Okay, here we go. You should be ready on the AP exam to receive hopefully a very general related rates problem. I put kind of one of the easier ones up here. Surface area of a sphere increases a rate of 8 inches squared per minute. At what rate is the radius increasing when the radius is 4 inches? So the idea is you have a sphere, and it's speaking of the surface area, and they would give you the formula for surface area, but of course, you all remember what the formula for surface area of a sphere is, right? 4 pi r squared. Good job. So if surface area is equal to 4 pi r squared, and you were to take the derivative, what is the derivative of surface area? Just surface area prime, right? And then, yep, you get 8 pi r prime. So the question is, at what rate is the radius increasing? So we're wondering what r prime is. And it says the rate at which the surface area is increasing is 8. So 8 equals 8 pi times, what is the current radius? Times 4 times r prime. So therefore, r prime is equal to 1 over 4 pi. And what is our label in? So we're measuring radius. If you measure radius, do you measure it in inches or inches squared or inches cubed? Just inches, right? And it is changing with respect to time. Again, we're looking at a rate, so inches per minute in this situation. Okay. You all good? Hi. Didn't know that happened. So didn't know Shelly wasn't here with us. All right. So we're not going to see these problems all the way through. We'll set them up. You should be able to handle area and volume. But of course, you're extremely familiar with those, aren't you? Okay, so this first question should look somewhat familiar. It says it wants to find this area bounded between x cubed minus x and negative x squared plus 1. Can you tell me which function is on top? Yeah, it's 1 minus x squared or negative x squared plus 1. That's the one on top. So you might have to be able to decipher which one is on top, which one is on bottom. And then this one on bottom here is x cubed minus x. So can somebody tell me how I determine area between two curves? Yeah, just top minus bottom. Good. Yep. So integral of the top, as you said, is 1 minus x squared. And I'm going to subtract the bottom, which is x cubed. And then as I distribute the subtraction sign, I will get a plus x dx. So how would I determine my bounds of integration? Yeah, you're looking from this spot here to this spot here, aren't you? Okay, because this is a dx problem. So you're going to set these equal to each other, or where's x cubed minus x equal to negative x squared plus 1? So we'll just go back to our algebra days, and you all know how to solve that. What do we do with our algebra? Get everything on one side, so x cubed minus x squared. Well, plus x squared, excuse me, minus x minus 1 is equal to 0. Ooh, 4 parts. What do we do? Starts with a G, rhymes with grouping. So I factor out an x squared, I'm left with x plus 1. And then I factor out a negative 1, and you get x plus 1. Factor out the x plus 1, and you are left with x squared minus 1. And hopefully at this point you can see that the solutions are negative 1, and positive 1. And notice how that confirms with our result here. It is kind of neat that back at negative 1, notice how the two curves, they touch tangent to each other. That shows a double solution. And then positive 1 you can see right there. So we're going to go from negative 1 to positive 1. So true or false, if I'm going negative 1 to positive 1, I could just go 0 to 1 and I could double it. Which is it? It is false. Why? Because the area is not symmetrical on both sides. I mean, if you were to divide it in half, that side's bigger than that side, right? Yeah. So you have to make sure that the area is symmetrical. In this situation, I could do it, right? Yep. So let's set this up. Is a volume by disk, it says the area by this and that revolved around the x-axis. So we're going to take this, revolve it around the x-axis. So I'm going to take a section of this area. I'm going to revolve it around the x-axis. I think I might bring the youngest two down tomorrow. Have them pull them. So you guys are going to be taking the test, not me. So what do you do? What's your volume for a shape like that? Close. That's a washer. Pi r squared, and then dx is our width, right? So that's going to give us that volume of that washer, so or that disk. So you got to know how to come up with that formula. Okay, you got to recognize that. And so now it's pretty straightforward for us. We just have to identify what r is. So what determines this radius right here? The function, yeah, 4 minus x squared, right? And so the volume of one of those things is pi times 4 minus x squared, quantity squared, dx. But we don't want one of them. We want an infinite number, so we slap on an integral. Good. So Colin is correct. He says in this situation, he recognizes that it is symmetrical about the graph. So you could go from -1 to 1, or you could go, I'm sorry, from -2 to 2, or you could go from 0 to 2 and double it. I'm going to go -2 to 2, and the reason why is in this situation, I'm not asked to actually evaluate it. You know what I mean? I'm not asked to evaluate it. I think that if you have to evaluate it, then going from 0 to 2 makes it easier to evaluate, right? But, you know, I'll just write it like that. Doesn't really matter. Okay, so if I take this thing and revolve it around x equals 2, so x equals 2 is like right there. I'm going to revolve this thing this way. What shape do you get? The washer. All right, see if we're back on track now. Who remembers the formula for the volume of a washer? Yeah. Remember the differences to those folks? Big R squared, little r squared. Good. All right, so I've got that. What's the thickness, dx or dy? dy, good. So I've got what do I got? Pi times big R squared minus little r squared dy. So let's interpret big R and little r. Notice how I'm going to use kind of my little kind of organizer I like to use here. So I've got that, and I've got that, and I've got this. So what makes up the center? X equals 2. What makes up this? Yeah, that's y equals x squared, isn't it? But the variable must be in terms of y. So I'm not going to write y equals x squared. I'm going to write x equals the root of y. And then what makes up this outside piece? X equals y squared. I'm happy about that. I now have a y in that situation, right? So what is my big radius? Remember, it is top minus bottom and right minus left. So the big radius is going to be 2 minus y squared. So we have pi times 2 minus y squared, that quantity squared, minus, then what is the little radius? 2 minus the root of y, quantity squared, slap on the integral, bounds, 0 to 1. Not too bad, huh? Flip it over. So we'll go over, so excellent question. The question from Jenna is about the evaluation. And so if you look at your FRQs and the different types of problems that you get for FRQs, the most common one is going to be motion. You know, so you know how yesterday we talked about like velocity and acceleration and stuff like that? That's the most common FRQ that you're going to get, okay? The second most common FRQ that you're going to get is a area and volume one, and I would say specifically volume. And so motion, and then number two would be volume. And then after that, the third one would be the fundamental theorem of calculus, where they're going to give you like a rate function. Rate is equal to something like, say, snowfall, like how much snow is accumulated over a given time. Might give you a table. The fourth one is going to be your slope fields and differentials. So we'll get to that as well. But you're like, why am I going through all this? I want to make the point here. Jenna asked about the evaluation point here, okay? And what's really important is this, is that a lot of times they will ask questions about volume in the calculator section. So your free response will be given a total of 6. The first 2 are calculator, and the last 4 are non-calculator. Get my point? So the deal is if it's in the calculator section, they will have you determine the result because you'll just plug it into your calculator. You know what I mean? But often, if it's in the non-calculator section, then they will just say, please write an integral that represents the problem correctly. You know what I mean? Sometimes they get kind of icky, you know what I mean? So, does that make sense? Okay, so, you know, we haven't covered everything, but we've covered really, I mean, these are the topics we've covered, okay? So, this is why I started. So, what do we really need to know? And, like, what's the absolute must things? You can see up here things like L'Hopital's rule, derivatives, power rule, product rule, increasing, decreasing, local mins and maxes. I mean, these are all things, I mean, it's kind of a little summary of our year, right? And that's the chief content that you're going to see on the AP exam. Now, it's like, what do we need the other 4 weeks for? Well, we need to start to really dig into those problems. But you guys now have a foundation and basis. One topic that the AP exam does get at that we got to make sure we know and just have reference with, and they're not going to necessarily ask it all times in this context, but is regarding the mean value theorem. And the mean value theorem says this, and this is kind of where we end with our general rule, and then we'll let you guys go to your AP problems and study them. But the mean value theorem says this, and I always come back to the graphical representation. Don't write this down, but suppose I have a function that has, say, this shape to it, okay? And we're going to look at it over a closed interval. So from this point to this point. Somebody describe the slope from the beginning to the end. Say anything about it. It's positive, okay? Yep, so the function's increasing, the first derivative is positive, okay? Maybe slope might be like, I don't know, close to 1, something like that. Everybody good with that? So the mean value theorem says, if you look at the slope from one endpoint to the other endpoint, there has to be a spot on the graph where the derivative is the same as the slope. So you tell me when I get to the spot where if I drew a tangent line, I would have a slope that would be the same as that. Yeah, I think that's a good spot. I know my line. Sometimes I feel dumb. Like, hey, do AP calculus, I can't draw a line. So anyway, so I would agree. And so that's point C right there. So when we do f of b minus f of a over b minus a, that computes this slope. And then when we set it equal to f prime of c, the derivative at point C, we're finding point C there. That's what we're doing. Everybody see that? And I would say that, I used to just think it was not a big deal. And as I go through AP Calculus, now I understand how that is definitely a stretch for a lot of people to really comprehend and interpret. So we'll look at the most basic kind of example of the mean value theorem. And we'll do 2 of them here. It says f of x is equal to that. And it says find C that satisfies the conclusion of the mean value theorem. That would be a typical kind of AP question you get. So what it's saying is that there's some value between -3 and 2 such that the derivative is the same as the average slope over the given function. So where would I start? You could take the derivative. Let's start with that side, though. What's f of b? How do I compute it? Plug in 2. 2 cubed is 8. Minus 8 is 0. Plus 2 is 2. Cool. And then f of negative 3, yeah, I plug in that negative 3, and I get negative 3 cubed, which is negative 27. It's going to be a plus 12, plus 2. Is that negative 13? So let's write this out now. What's the derivative? 3x squared minus 4 equals, what is f of b? 2 minus f of a. So plus 13 divided by, yeah, so 5, right? So 3x squared minus 4 equal to, yeah, 3. So I'm setting this up to try to find that value c that sits in there. So how do I solve this? Yeah, 3x squared is equal to 7. So x squared equals 7/3. X equals plus or minus the root of 7/3. So is there one solution, two solutions, or no solutions? Let's figure out what the square root of 7/3 is, folks. I turn my calculator on, and I go square root of 7 divided by 3. And I get 1.57. So does positive and negative 1.53, excuse me, do both of those sit in there? Yes, so there are two solutions. But it's possible that only one of them would have fit. Then you would have only had one solution. To get my point? All right. And to be clear, on the AP exam, you don't have to simplify a radical. Like, you can just leave it. Okay? Let's try trig function. F of b. What is our b value? 3 pi. So 3 pi divided by 3, pi, sine of pi, 0. Then I have f of 0. Sine of 0, 0. So let's write this out. What is the derivative of 2 sine of x over 3? Chain rule. Derivative of the inside, what's the derivative of 1/3 x? 1/3. So everybody see I'm going to get 2/3 cosine of x over 3. And that is equal to, we're going to have 0 minus 0 over 3 pi. Or in other words, 2 over 3 cosine of x over 3 is equal to 0 over 3 pi, which is just 0. How do we begin solving that? 3/2. I get cosine of x over 3 is equal to 0. Where is it that cosine is equal to 0? Pi over 2 or 3 pi over 2. So x over 3 is equal to pi over 2, and x over 3 is equal to 3 pi over 2. What do we do to both sides? Multiply by 3, and we get x is equal to 3 pi over 2, or in this situation, you can see 9 pi over 2. And hopefully you begin to understand there's actually an infinite number of solutions to that. It just depends on how many times we go around the unit circle. So hopefully you can find one that sits in that interval. Do one of these sit within that interval? 3 pi over 2 sure does, doesn't it? So therefore, x equals 3 pi over 2. There is one solution. Yay! Good job. You guys did really well. Thank you for your efforts. So what I have for you now is just take out that thing that looks like this. And if you could give me some feedback, and I will not be angry with you. You will not hurt my feelings. Okay, we're in a safe place to give feedback. A couple years ago, we just did the practice problems and gave a few little notes. This year, I gave you the review and then tried to practice problems. Do you think that it was worth us to spend a time going over some review and then try them? Or do you think I should just skip the review and throw this at you? Thoughts? Okay. So that what was missing from my brain when I went through it, some of the previous years, was that I just figured we remembered all those things. I know. I used to be a bad teacher, and now I'm working on my derivative is positive. Okay, I'm working my way back. It's not funny. Whatever. Okay, I'm going to talk loud now because of you. All right. So anyway, I hope that going over some of these problems that we did with the review help you, set you up for success here. And I get that, like this mean value problem is completely different than what we just did, right? But at least you have a general idea of what the heck the mean value theorem actually is, right? So what I want you to do is, I don't think that we answered this mean value theorem problem. You probably just guessed, right? So maybe go back and look at this mean value theorem problem there. And then if you flip it over, you're going to see this is another good kind of problem to try. At 15, if you haven't looked at that. And then where did we leave off? Kind of like right here, the area one. If you could then, do 19 and 20 and kind of, kind of finish some of those off. Okay. Be nice to, Monday come on back and try to go over these answers together before we venture into our new piece. Okay. I think. Yeah, that's a lot, isn't it? Yeah. How about we go up to the nope, we're not going to have success with that. So let's go up to this, 26. That'll be a good spot. Okay, if you could do that, that would really cover kind of what we've gone over. The others we're going to have to kind of just ditch for a little while. We good? Look at that, sun's kind of out. It's going to be nice this weekend, and then on Monday and Tuesday it's supposed to be like 55, and then Wednesday we've got this big storm coming in out of the Rockies. It's possible we might get significant snow, measurable snow by Wednesday evening. So we're hoping Wednesday during the day is okay, but it's we'll have to see what the storm does.